about for a P-chart example to begin with. Let's suppose that I have a machine. Let's talk about an injection molding machine. Where I have, say, let's make it 10 cavities. On a die. So at each stroke of the machine, I make 10 plastic parts. Let's further suppose, so you can imagine here, I don't know how we want to lay these things out, but we might lay them out, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And every time that the machine is charged, these cavities are filled with plastic. We get 10 parts. Now, let's suppose, for sake of argument, that cavity is perfectly bad. All the other cavities are perfectly good, but that one's perfectly bad. There's something, the thing was just made wrong. What are we going to see if we look at p-hat values over time? Well, p-hat values, there'll be one bad guy out of 10 all the time. So p-hat values will look like 0.1, 0.1, 0.1, 1 in 10, 1 in 10, 1 in 10, 1 in 10, if I'm so foolish as to simply grab one item from each of those 10 cavities and together call those things a sample. So p-hat values will look like this if I call 10 made at one time a sample. You see, what I've really got here is not one machine. I've got 10 channels. I've got 10 production channels. So I have 10 parallel production streams. If I sample them in systematic fashion, then consistent differences will make plotted p-hats look too consistent. That is, p-hats won't vary like binomial variables do. They'll be consistently 1/10, 1/10, 1/10. In a measurement context, if I had this same 10-headed machine, and 9 of 10 of those heads were producing widgets with diameters that are, say, 5 plus or minus 0.001, and this guy was producing widgets with diameters 6 plus or minus 0.001. And think about what I'm going to see if I was so foolish as to sample these 10 guys regularly take 10 items and call them a sample when they're not really a sample? Well, I'd see essentially 9 of these and 1 of those. The 9 5s would give me a total of 55. The 6 would give me a total of 61. So I'll be seeing X bars will be 5.1 with very small variation. At least in comparison to the difference between this 5 and 6. Okay, that is, if I was thinking about making range charts or whatever, the ranges will all be essentially 1. Okay, the difference between a 5 and that large value 6. The point is that if I have variation that's too small, one thing that might be going on is I might be sampling upstream different product streams in a systematic way, measurably different product streams in a systematic way, producing too little variation in a plotted statistic. And the jargon that people have invented for that is to call such a possibility stratification. So it's a discussion of this idea of stratification. The idea here is that one should monitor parallel streams individually. That is, it does not make any sense to think of that 10-headed machine is one entity. What I ought to do is monitor head number 1, head number 2, head number 3, head number 10. Cavity number 1, cavity number 2, cavity number 3, cavity number 10 individually. If I foolishly try to monitor them all at once by treating the 10 heads as giving me a single sample, I'm setting myself up for stratification and unnaturally small variation in a plotted statistic coming from consistently different inputs to that plotted statistic. And I will not have this, and I will basically will miss, if I'm so foolish as to ignore the stratification, I will miss the fact that there is a fundamental difference between this guy and all of the others. I'll miss the fact that there's a fundamental difference between that cavity and all the others. I will miss the fact that there is a consistently bad head or bad cavity in this machine. Okay, so that's a bit on stratification.